right, hi everyone. It's not switched on, is it? There we go. Hi everybody. So I just wanted to give a really brief overview of an interferometry study I've been working on in Kamchatka, Russia. And I gave this talk a little bit of a cheesy title. It's called Deciphering the Whisper of Volcanoes. And this picture you see here is, well, a picture from ISS, or taken from ISS onto the erupting volcanoes on Kamchatka. So that's the Klyuchevskoye volcano group. So the motivation to work on volcanoes is obviously always to improve volcano eruption forecasting. And to date, this has been done with mainly three big precursors, which are volcanic inflation, which we can measure via GPS. So we measure ground deformation via GPS. Then there may occur temporal variations of gas emissions, so we're talking about chemical variations, and also we often observed an increased seismicity preceding eruptions. However, all of these three indicators may or may not occur in any given combination to our eruptions, so we're always looking for new measures that can precede eruptions. And what has been used lately is a velocity change. So we're looking at changes in the seismic velocity in a close vicinity to the volcanoes. And here are two papers which have successfully demonstrated that there were velocity changes preceding eruptions or preceding inflations of the volcanic edifice. The way we retrieve dB over V is from ambient seismic noise. So it's just noise interferometry. Essentially, we retrieve a Green's function and for a certain time period, and then we compare these Green's functions and the changes of the Green's function with each other using the trace stretching method. So that's just simply correlation function comparison in the time domain. And an issue in Kamchatka that we're facing in particular is that we have very fluctuating noise fields. Here's a spectrogram of one of the stations that we have there. So we have more than 100 stations available. And here we can really clearly see in these red boxes, you can't see my mouse pointer, I'm going to do it this way. In these red boxes here, we've got these bright spots occurring mainly between like 0.5 and 5 hertz. And these are volcanic tremors that we can see. So we have constant volcanic activity, and this volcanic activity has been shown to shift location, and this essentially breaks our assumption in interferometry. And if we now would try to compute correlations with this, it looks pretty ugly actually. So we get this really like differing Green's function estimates, and using these, I mean, they're not comparable to each other, so we can't really apply any interferometric method to this. And the way we deal with this is that we use a clustering algorithm to separate time periods in which the tremors stay stable or in which the noise field stays stable. So essentially we use a hierarchical clustering algorithm and then cut off at 5 different clusters. So we get 5 different clusters here, and looking at the temporal distribution, it gets really interesting because we can see they all occur together. So we shift from one cluster to the next cluster to the other cluster. And again, here I've plotted the average correlations, so essentially the average Green's function estimates per cluster here. And looking at these in detail, we can see they're very different, so they're markedly different. And there are hardly any phases we can track through all of these. So again, this confirms essentially our observation that we can't do any interferometry here. However, given that we have this temporal distribution that is very close to each other, we decided to essentially pick one time period, throw in all the data that we have there, and do one separate interferometry study per time period that we've given here. Looking at the results that there's another animation happening here. So in these time periods, actually, they coincide with these time periods of volcanic activities that have been found before. So here's a paper by Cyril Journow and colleagues, who essentially use this spectral width, that's what they call it, to find the periods of strong volcanic activity. And we can exactly see these time periods in our clustering again. Now, finally, looking at the dV/V results that we observe from this. So we have 3 groups of stations we're looking at here, plotted as circles, squares, and triangles, respectively. And here we can see velocity changes occurring at different parts of the time. So one of them is this big earthquake, local earthquake striking in the south that induces this damage and recovery. We see environmental effects, so we see precipitation plotted in blue here, like a bit hard to see, that induces a velocity drop, very short, and we can also see a long-term effect of an increase in velocity, and this is related to the snow load plotted here in gray that is increasing constantly, and the pressure of the snow essentially induces the compaction and a reduction of pore space, so increase in shape velocity. And lastly, what is maybe what we're the most interested in, what we can see here is that we see an increase towards the end of this time period we're looking at, and especially at the circle and the square stations. And these are the stations that are very close to Bissimiani volcano, which is believed to have the start of an eruption circle at this time. Just conclude real quick. So we were able to obtain stable and high-resolution dV/V estimates by using these high-energy tremor periods windows, and by sticking to these time periods and combining this with the spatial stacking. We see response to the seismic environmental factors, and something that we believe could perhaps be a sign of inflation at Bissimiani volcano. And if you want to come to my poster, we can also discuss about the different dV/V responses depending on the location at the network. And, well, also a little bit of advertisement here. There's, I coded a Python software that you might want to use if you're not entirely happy with the solutions that exist so far. And also, if you're in EGU, which you probably are, I've got the EGU upload material as well, which shows even more details than my poster does. Thank you very much.